In this video, I'm going to talk about predictor effect plots, which I find a helpful way of interpreting a multiple linear regression model using graphics. So transformations and interactions, although they can enhance our ability to model multiple linear regression relationships, they can also make the resulting models quite difficult to understand and interpret. And so these predictor effect plots that I'm going to talk about in this video are one approach to interpreting such models. In particular, what they do is they plot how y changes as each predictor changes and all the other predictors are held constant. And so in a way, they are a graphical representation of the regression parameters in a model. One word of caution here is, although I call these models predictor effect plots, that doesn't imply any kind of causal relationship. So just bear that in mind as we go through this presentation of predictor effect plots. They're modeling associations but not causal relationships. So to illustrate predictor effect plots, I'm going to use some credit card data. So we've got data here where we've got credit card balances, average purchases, average amount of money spent on housing expenses, and then we've also got information on whether the credit card holder is a renter, which is R, or a homeowner, which is H. And then we've also got information on gender, so we've got males and females in our data set. So that's a description of our data that we have. And so we've got two quantitative predictors and two qualitative predictors that we are coding using dr, which is the indicator variable for renters rather than homeowners, and then dm is the indicator variable for males compared with females. So I'm going to create all of these additional predictor terms. So I've got interactions between each of the indicator variables and each of the quantitative predictors, and then I've also got two square transformations there of the quantitative predictors. So I'm going to start with this model here. So it's got all of the predictors plus all of the interactions plus the two squared terms. And if I look at the coefficients table, and in particular I look at this column of p-values, I can see that I've got some high p-values here, bigger than our usual 0.05 significance level. So it looks as if my model is a little overcomplicated, and I could probably simplify it by removing some of the high p-value terms. So, for example, house squared doesn't look as if I'll need house squared if I have all the other terms in the model. It's got a relatively high p-value. Also, dm house, maybe I don't need that interaction, and dm perch, maybe I don't need that one, and then dr perch, maybe I don't need that one either. I'm going to keep these four though. Okay, even though I might say, okay, well dm, well actually dr has the highest p-value of those four, doesn't it? but I'm not going to consider getting rid of dr because it's involved in some of the higher order predictor terms. So dr house has a very small p-value, so because I'm going to definitely keep dr house in the model, I'm going to keep dr and house in the model regardless of their p-values. Okay, so let's fit that model with those predictor terms that we just talked about removed, and then if we summarize this model, then everything has a significant p-value at the 0.05 level except for dr, but that doesn't matter because I've got dr house in the model, so I'm going to retain this for hierarchy reasons. Let's just do a quick nested model f-test to make sure that what we did was okay. So yeah, we've got a p-value bigger than 0.05, so I cannot reject the null hypothesis that the regression parameters in the more complicated model are all 0. So in other words, if all those regression parameters are all 0, then I don't need that more complicated model. I can just remove those particular predictor terms, and I can go with my reduced model, which is model 2 in this case. Okay, so model 2 is represented in this table of coefficient estimates, so 19.09 for the intercept, minus 23.92 for the regression parameter that goes with dr, and so on. So that's what I've summarized here. Can't seem to highlight the whole thing, but you can see it down there at the bottom of the slide. I've just written the predictor terms in a slightly different order, but the numbers are all matching the numbers in this table here. Okay, so what does all this mean? How does Y, so the average outstanding monthly balance on someone's credit card, how does that depend on all these predictor terms, x1, x2, dr, dm, and what role does this interaction have, and what role does this quadratic term have? So one way to understand the relationship between y and all the predictors is to think about each predictor in turn. So let's think about x1 first of all. So in particular, I'm going to think about what I'm calling the x1 effect. So what that means is I'm considering how y, which is the balance, changes as x1, which is the amount of monthly purchases, as that changes. So what I can do to understand this question is to isolate the change in y when I hold everything else fixed. So everything else in this context means x2, whether someone's a renter or a homeowner, and whether someone's male or female. What should I hold these other predictors fixed at? Well, I could hold x2 fixed at the average sample value of x2, so the mean of x2, the sample mean of x2. I could hold the renter status fixed at dr equals 0, and then I could hold the gender constant at dm equals 0. Okay, so that's what I'm going to do. I'm going to hold x2 constant at the sample mean, I'll hold dr constant at 0, and hold dm constant at 0. So what I'm looking at here is I'm looking at how y changes as x1 changes for a female homeowner who's got a value of x2 equal to the sample mean. So to do that, what I do is I take these values and I plug them into my regression equation. My regression equation was this equation down here. Okay, so I plug in the mean of x2 here, I plug in dr equals 0 here, dm equals 0 here, and so on. So if I do all that, I'm going to end up with an equation that, if I do some calculations, I can simplify. So for example, this will simplify to 0. This piece will simplify to 0. This piece will simplify to whatever 5.335 times 5.598 is, and so on. And then what I'm going to do is I'm going to collect all the pieces together that go together. So for example, 19.094 can be combined with a minus 29.865, and I get minus 10.77. And then I've got 18.63x1, I can't simplify that anymore, and I've got minus 0.92 times x1 squared, I can't simplify that anymore. So I've ended up with an equation of just x1. Okay, so this is telling me how y changes as x1 changes and x2 is held constant at this value, and renter status is di equals 0 and gender status is dm equals 0. And then what I could do is I could draw a line graph with this function of x1 on the vertical axis and x1 on the horizontal axis. So that's what this graph is here. On this axis I've got x1, the horizontal axis. On the vertical axis I've got this function that we just calculated. And you can see that it's a curved line, it's a quadratic function of x1. And so what this is telling me, it's telling me that as purchase increases, the effect on someone's average monthly balance is to increase. So that makes sense, right? The more people spend, then the more their balance goes up. But as purchase increases at a low value of purchase, so say from 1 to 2, the effect on average monthly balance is quite dramatic. It goes up quite a lot. The line is quite steep on this side of the graph. Whereas if I increase perch from say 8 to 9, the line doesn't go up very much relative to how much it goes up on this side of the graph. Okay, so if I was to try and summarize that in words, I could say, so remember again that this was for dr equals 0 and dm equals 0, and dr equals 0 is homeowners and dm equals 0 is females. So what I could say is that high spending female homeowners with average monthly housing expenses, that's x2, tend to carry a higher credit card balance than low spenders, but those balance increases become smaller the more that is spent each month. Okay, that's because the line is curving this way. If I wanted to quantify that, then I could just do a little bit of arithmetic. So for example, when x1 increases from $200 to $300, so that's from 2 to 3 on this graph. So what I'm doing is I'm calculating what is the difference between this value on the vertical axis and this value on the vertical axis. Okay, I can calculate that by just plugging in 2 and 3 into this formula and taking the difference. Okay, so that's what this is here. I'm plugging in 2 and 3 and taking the difference, and what it amounts to is about $14. Okay, so on this graph, the vertical distance between here and here is about $14. And then I could do a similar thing at the high end of the graph, so from 800 to 900. So from here up to here, the curve only goes up a little bit, and if I do the math, That comes to $3. Okay. So what's so special, you might ask, about female homeowners with an average monthly housing expenses? Well, nothing. I could just as well hold the values of x2, dr, and dm fixed at other values to focus on another kind of group of people. For example, I could look at male renters with an average monthly housing expenses. Or here I've got an example. You could look at male renters with a value of x2 equal to 4. Okay, if you ran through this whole exercise with those values instead, so I would have 4 here, and I would have 1 here, and I would have 1 here, and then I ran through this plugging in and simplifying process. The math is going to be a little bit more complicated, but I'll end up with an equation again, and what will happen is that these functions of x1 and x squared will be the same. The only thing that will differ is this piece here. So I'll end up with the same graph, but the numbers on this axis will just change. So it's as if this graph is just shifting up or down, okay, depending on which particular kind of person I'm looking at. And then if I do this bit of math here and look at the difference as x1 goes from 200 to 300 and as x1 goes from 800 to 900, I'll end up with these exact same numbers. Okay, so what this means is that vertical distances between the points along the line represent changes in y as x1 changes for all individuals in the population, not just specific types of individual, but for all individuals. So in that sense, this graph is kind of universal. Okay, so that's the x1 effect. Let's do a similar thing for the x2 effect. It's a little bit more complicated for x2 though, because we've got an interaction term to worry about. Okay, so let's hold x1 constant at its sample mean, and then we'll hold gender constant at the reference level again, dm equals 0. So we're talking about females initially, and then we've got our regression equation, and we're just going to plug in 4.665 wherever we see x1, and we'll plug in 0 wherever we see dm. Okay, so we got the 4.665 here, and then we've got the dm equals 0 here. Okay, and then I'll do the math, and then I'll gather like terms. So for example, if I take these two numbers and subtract this one, I'm going to get this. And then I've still got minus 5.33 x2, and I've got minus 23.92 times dr, and I've got 17.58 times dr times x2. Notice I didn't plug in dr equals 0. And the reason is because I'm trying to figure out how y changes as x2 changes. And I've got x2 here, and so if I plugged in dr equals 0, this piece would go away, and I'd lose the relationship that y has with this interaction term. Okay, so that's why I haven't plugged in dr equals 0 here. I've left that in my formula, in my equation. Okay, so this is what I'm calling the x2 effect. What is this? Well, it's a function of x2 and dr. And remember, dr is an indicator variable, so it only takes values 0 and 1. So one way to think about this function is it represents two possibilities. It represents a relationship with x2 when dr equals 0. So if dr was 0, these two pieces would go away, and I'd be left with this straight line, 85.92 minus 5.33 x2. And if dr equals 1, I would have 85.92 minus 23.92 as an intercept, and I would have minus 5.33 plus 17.58 as a slope with respect to x2. So if I was to put that on a graph, it would look like this. I've got a line for renters when dr equals 1, and I've got a line for homeowners, which is when dr equals 0. So this line here, the homeowner one, this is the line 85.92 minus 5.33 x2. And then this line for renters is, this has an intercept of 85.92 minus 23.92. So it has an intercept of 62, this line, and it has a slope of minus 5.33 plus 17.58. So it has a slope of 12.25. Okay, so this predictor effect plot for x2 shows me that for homeowners, as their housing costs increase, they tend to carry a lower balance on their credit card. Whereas for renters, as their housing costs increase, then they tend to carry a higher balance on their credit card. Okay, so that's a summary in words of what this picture represents. At this point you might wonder, well why? Well, how could this be the case? It's easy to imagine that renters might carry a higher credit card balance, than homeowners. If you imagine that perhaps homeowners tend to be perhaps more wealthy than renters on average, and so perhaps renters have less access to credit, and so they need to carry a higher balance from month to month. Perhaps that's one possible scenario here. Why is it that renters' balances increase as their housing expenses increase? Well, as their rent goes up, again, that means their credit is going down, perhaps, and they're just needing to carry a higher credit card balance because they don't have as much access to money because their rent's higher. What about what's one possible reason why homeowners' balances decrease as their housing expenses increase? So for them, their housing expenses are going to be tied to their mortgage. So what's one possible reason why someone's credit card balance might be higher as their mortgage is lower? So for example, I'm thinking about the homeowners now. People on this end of the graph have lower mortgages than people at this end. Someone perhaps with a higher mortgage, perhaps their house is more valuable, perhaps they have more access to cheaper forms of credit than running up a credit card balance, and so they don't need to carry as much of as high a balance on their credit card because they have cheaper forms of credit than someone with a low mortgage. Who knows? I'm speculating, but that's something that this kind of plot allows you to do. It shows you what the model is doing, and then you can come up with, or you can investigate, or it might raise questions about how can you explain the story that's in the graph. And then we can do a similar thing to what we did last time as well, is we can just do some math and look at how an additional $100 in housing expenses affects the different types of person. So for renters, an additional $100 in housing expenses tends to increase the monthly balance by $12. That's because the slope of this line is 12.25, I think we calculated it as. Whereas for homeowners, it decreases the average monthly balance by $5, and that's because we've got a slope of minus 5.33 there. We could also look at the difference between renters and homeowners. So what I'm looking at here is the difference between the vertical distance between these lines. So it increases as housing costs go up, and that's given by this function here. So all I'm doing is, again, plugging in dr equal 1 for renters, dr equals 0 for homeowners. I've got my two equations, and then I'm just taking the difference between them. A lot of these pieces just cancel out. For example, this piece cancels out, this piece cancels out, and so on. And I'm left with just this function of x2. And so that represents the difference, the vertical difference between these two lines. It's a function of x2. It increases as x2 increases. Putting it into words, renters tend to carry higher credit card balances, and the difference between it becomes greater as average monthly housing expenses increase. And then finally, we could look at differences in Y between males and females. So run through a similar exercise, plug in D1 equal 1 and plug in D1 equal to 0. Take the difference between the two equations. A lot of it cancels out. In fact, everything cancels out except this term here. So what does that mean? Well, remember, males are D1 equal 1, females are DM equals 0. So this is negative 10.68. In other words, males tend to carry lower balances on their credit cards than women. In this sample, I'm not saying in general, but just in this sample, by about $11 on average. So what I've done in this video is just run through an example of how predictor effect plots can help us interpret the final regression equation from multiple linear regression model, and how we can look at those graphs and begin to tell a story about what the model is telling us. Okay, so that brings us to the end of this video, and that actually brings us to the end of this entire series of videos. I've worked through chapters 1 through 5 in the textbook now, and that brings us to the end. There are a couple of additional chapters in the textbook, so chapter 6 covers some case studies, and chapter 7 carries some extensions to the multiple linear regression modeling that we've covered up to this point, but I'm not going to cover those in videos at this point in time.